You'll notice on the board that I only have one of your aims written for today. We actually have two aims because you'll notice two completely different things on the different sides of your teacher time today. One of them looks very much like yesterday's work, and one of them, well, it just looks new. So we are going to follow up on yesterday's lesson by looking at some slightly more complicated problems and just putting in the last couple pointers to make sure that you guys are 100% successful on that. So after you're done writing down the first aim, let's go ahead and write down the second aim, and that's to be able to find the square root of a number. That's just a repeat of yesterday's aim. So our second aim for today, Kipsters will be able to find the square root of a number. So all of the key points that we developed today are actually going to be in the second half of the lesson, because all of the key points for the first half of the lesson we did yesterday, we're just doing a little bit of review here. And I want to look at these problems and think about strategies that you can use, whether it be on a test or in the real world, to make sure that you get these problems right. So the strategy that I highly suggest that everyone use on a test, because you're going to be doing more than one of these problems, is I suggest go ahead and listing all of your perfect squares. So this is a challenge for you guys. I want you to go as far as you can listing your perfect squares. I'm going to give you about 1 minute to go through and list as many of your perfect squares as you can get through. Hopefully you have a list that looks something like this. Okay, so you'll notice that as I went down and I did my list, I got to 16. And I put some dot, dot, dots. That meant that there are definitely some numbers in there that I don't know, that if I end up having to use those numbers, I'm going to have to actually do the work for those. But I do know 20 and 25, and so I can use those to estimate. So at the very least, I can say, all right, at least the number that I'm going to be looking for is between 20 and 25. So I can start with my calculations there rather than starting at, 45 or anything like that. So the way that we're going to use this, and the way that this is so helpful, is when we start looking over at problem number 1. Here it says the square root of 148. So I'm looking here and I'm thinking to myself, what two perfect square roots is it between? Well, this is really easy now that we have this list, because I'm coming down, 64, 81, 100, 121, 144. That's really close, 169. So it's between these two. Makes it really easy to go square root of 144. That's 12. Square root of 169. That's 13. Our answer must be that it's between 12 and 13. Makes it super easy. So looking at the next one, square root of 200. Want to keep coming down the list. What's my perfect square right before 200? Oscar? So the square root of 14. So he's saying square root of, 196. That's 14. So on the other side is the 225, which has a random extra number on there. Square root of 225, which is 15. Now the last one, square root of 324. Now I see that when I get the square root of 324, that's between my 256 and my 400. But there's a handful of whole numbers in between there. So I'm just going to have to start doing the work. So I'm going to go ahead and do 17 squared off to the side, which is 17 times 17. Which is 9, carry the 4. 1, 1, 0, 7, 1, 9, 8, 2. So I get 289, so that's still going to be less. So I'm going to have to go until I pass it. So I'm going to do 18 times 18 next. I get 4, carry the 6. It's 144. 0, 8, 1. And I get 324 exactly. Now, I get 324 exactly. What does that tell me about the square root of 324? That it is a perfect square. And so that perfect square, the square root of 324, is indeed 18. Same thing. So this is just a helpful strategy for you. I would say if you only have one square root problem, this may or may not be useful to you. But if you're going to be doing several square root problems, like on the CST, or like on your benchmarks, or like on your test that is on Wednesday, then it may be useful. Okay? All right. So that was really just a quick refresher, quick reminder, and a strategy for you to use for that. Our main aim for today is talking about rational versus irrational numbers. And before I tell you my story that I think helps represent irrational and irrational numbers for me, I want to think about a couple things that we have already talked about. Okay, so we've talked about fractions and how all fractions either terminate as a decimal or create a repeating decimal. Okay, all fractions either terminate or repeat. And we talked about imperfect square roots, and the reason why we estimate them as between two whole numbers is because we can calculate those numbers out and get closer and closer and closer and closer and closer and closer, but we can go out thousands and thousands of decimal places and we'll never get something that multiplies back out to be exact. Okay? So imperfect square roots do go on forever if we think about them as a decimal, and they never repeat. All right? So when we're thinking about rational versus irrational numbers, I usually think of something that happened to me on the BART one day, and I usually think about it as three different people. Now, you're going to have to bear with me for a second. I did promise that I would tell this story in a British accent. So, for those of you who understand what a British accent is or know British people, I really apologize. This is going to be terrible, but I made this promise like a week ago and I have to fulfill it. So, please, maintain your calm while you listen to my terrible British accent. Okay, so, calm. So, a lot of times when I'm on the train, I run into a bunch of different people. I really think about them as three different type of people. The first type of person that I'm talking about always comes in, they say, "Hey mate, how are you?" And I say, "I'm doing just fine." And then they stop talking to me and they sit down. I think about that person, they're a terminator. They terminate, they stop the conversation, and we move right on. This is way more Australian than it is British, so I give you my very worst impressions here. So the next person comes in, sits down next to me, and they want to talk about baseball or football or whatever. American football, it doesn't really matter. And so this person makes sense to me. They start talking to me, and I say, "Oh yeah, I like the Giants. They're pretty cool." And he starts talking to me about Pablo Sandoval and Tim Lincecum and all these other guys, and I say, "Oh yeah, they're cool too." And then he just keeps talking about the Giants and baseball, and this makes sense to me. He's got this pattern going for him, that he's just talking about the same thing, and this makes sense. He just keeps going on and on and on forever, but at least he's talking about baseball. And then there's this third guy who just drives me absolutely bonkers. He comes in and he sits down next to me, and he says, "Hey, how are you doing?" I'm like, "I'm doing good." He's like, "The weather's really great outside. You know what? I really like the Giants, and you know what? I like football too. How are your shoes? Those are very nice shoes." And so this guy just keeps talking the entire time. Just the entire time. And I get completely off the BART train, but there's no rhyme or reason to what this guy's talking about. He's talking about one thing, he's talking about football, then he's talking about scissors, and then he's talking about pencils and projectors and students in class and learning and math and then binders and baseball and football all over again. There's no repeating pattern to what this guy's talking about. So it's just completely bonkers. And so I said to myself, this guy is really irrational. He's crazy. He just doesn't make any sense. And so that's how I start thinking about numbers. I think about them as the three guys on the train. The first guy, he comes in, he says hello, he He sits down. He's terminating. He's like a terminating decimal. That totally makes sense. That's totally rational. Next guy comes in. He really wants to talk about baseball. And he's going to talk on and on and on and on to me about baseball. But at least that makes sense. At least he's got a pattern to what he's talking about. And then there's this third guy. This third guy comes in, and he wants to talk on and on and on and on. And he's not going to stop talking. But there is no pattern to what this guy's talking about. There's like no rhyme or reason to what this guy's talking about. He's just talking about it. Raise your hand if you sat next to this guy on a bus or a train at some point. Yeah, there's always that guy. There's always that guy on every train. So that's the guy I think of as irrational. Okay, the other two guys, sure, the one guy's talking on and on and on forever, but at least he's talking about the same thing. He makes sense to me. He's rational. So I think about that when I'm thinking about rational and irrational numbers. So when we look at fractions, we say that fractions either terminate or repeat as a decimal. So are fractions rational or irrational? Based on the story and the definition that we just gave. Are fractions rational or irrational? What do you think? William?
I think both.
Okay, why do you think both?
Maybe one fraction isn't and one fraction is.
Okay. What do other people think? Yes, sir.
That is
Imperfect?
I mean,
So based on the definitions of the people that I met on the train. What do we think about fractions? All fractions, we just said they either terminate or they repeat. Genesis. So irrational is like the third guy on the train. What do you think?
I think they're rational
Go ahead, because.
because they're not like going into something else, but they're either keep going about the same thing or like they're repeating.
Yeah.
Or
So
they just stop.
what I hear her saying is that these are rational. And indeed she's right. All fractions are rational because at some point they either terminate or repeat, like those first two guys on the train. Those two guys are rational. They make sense. One of them stops talking. The other one talks on and on and on. That's totally fine because at least he makes sense. He's talking about baseball. Now, the third guy is kind of like our imperfect square roots. If we calculate those imperfect square roots over and over and over again, we just keep calculating them out further and further and further, we're never going to find an exact calculation, so that decimal is going to go on and on and on forever, and it never repeats. So imperfect square roots are like that third guy on the train, and so they are what type of numbers? Genesis? Irrational. So imperfect square roots are irrational. I'm also going to add one other number to kind of your list of things that you know as irrational numbers, and it's a number that you learned about last year when you were working with circles. Does anybody know a very special number you were working with circles? Andrea? Pi. So I don't know how much Ms. Wilcox taught you about pi, but pi is a number that is equal to 3.14, and this is where most of you stopped, and this is a rounded number at 3.14. It's 3.14159, blah, 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 blah. The number goes on and on and on and on forever. There are people who are calculating pi out to like the 100 millionth decimal place right now. And at this point, it doesn't repeat, nor does it stop, obviously, because they're still going out and out. So pi is irrational because it goes on and on and on forever and doesn't repeat. There's no pattern to it, okay? All right, so we know what a rational and irrational number is now. Now we need to start looking at some of these examples and defining for ourselves whether a number is rational or irrational. So looking at the square root of 16, we need to think about what the square root of 16 is. Now, are we going to label that rational or irrational? And be prepared to explain to me why you chose that number. Winter. Okay, so you're telling me that this is equal to 4. That's the excellent work that I definitely want to see. So if we know that the square root of 16 is equal to the number 4, does that make the square root of 16 rational or irrational? Jack. Rational or irrational? Be clear.
No.
Okay, so I've got you thinking here. Make sure that you're sure of yourself. ECs. Rational. Why? Because it doesn't go on and on forever. So when we look at this one, it simplifies to this very exact number. 4, period. Dot, termination. Okay, this number is rational. Because it terminates. So this is a perfect square root. It becomes a terminating decimal. 1/2. What do we think? Rational or irrational? Yeah. Why? How did you figure out that it terminates? What did you do? Just, I know you got it.
I turned it into, decimal.
Yeah, she turned it into a decimal, 0.5, and she says it's rational. Because it terminates. So we have 2 examples in a row that are rational because we know they terminate. Square root of 7. What do you think about that one? Damien. Okay, and why is it irrational? Because it repeats? Did you want to change that thought? Or were you happy with that? You are unhappy with it? Genesis, what do you think?
I think it's irrational because it doesn't have a perfect square root.
Okay, so it's irrational, and I'm going to put together some thoughts here. Because Genesis says it is an imperfect square root. Imperfect square root, which goes on forever without repeating. So it actually does not repeat. Okay, so imperfect square roots will not repeat, and they go on forever. So that makes it irrational. That is our definition of an irrational number. It goes on forever without repeating. And lastly, 2/3. Yang. Okay, so he says that it's 0.6 repeating. It's the same thing, so it is rational because it repeats. Which guy on the train is this? 1, 2, or 3? Which guy is this? Yeah, repeating. So this is the guy who, he came on and he kept talking about baseball. That's fine. He had a pattern to what he was doing. So that totally made sense to me. So this guy is rational. Now, I want to look at these two really quickly. I'm going to put a quick star next to them. You don't need to do this. This is just so I can indicate which two problems I'm talking about. Now, looking at the two problems there, we said that both of them were rational, and one of them we changed them both to decimals. What could we have used? What information that we already know could we have used to determine that it was rational without even changing the decimals? What have we already said today and previous days that we could have used as our determination that these numbers, 1/2 and 2/3, were definitely going to be rational? We didn't even have to change it to a decimal. What have I said? Isaiah.
All fractions are either terminating or
Perfect. So you could have used as your argument here for these, instead of saying it's rational because it terminates, you could have said it's rational because all fractions terminate or repeat. You wouldn't even have to do the work, the division, to change it to a decimal. That's totally fine, because there are some fractions that you're going to run into that if I gave you the fraction 234 over 1036, that I'm pretty sure you wouldn't want to do the division there to prove to me that it repeated, right? It would be a lot easier to just say, you know what, Mr. Boots, I know that fraction is rational because all fractions either terminate or repeat, okay? All right, let's hit those key points before we move on today. I have written one key point, however, I think the last class came up with 3, which I think is perfectly appropriate. So, I'm looking for some key points, and we'll start with Mr. Posey.
all fractions either terminate or repeat.
I'm going to add on to that just a little bit. He says all fractions either terminate or repeat. And what type of number does that make them, Isaiah?
That makes it rational.
Rational. So all fractions are rational. Because they terminate or repeat. All right. Other key points. So I think Isaiah's key point is great. I think, however, because of the way he worded it, we ended up with 2 key points, which is totally fine. That's the way the other class did it. Genesis.
You could put squares around imperfect squares because that's always where
Okay. So she wants to say, hey, this is definitely a key point here. This gives us our definition of what irrational numbers are. Imperfect square roots go on forever and do not come to an end. And most importantly, that's also our definition for an irrational number. Okay? So I think that's totally appropriate to add as our second key point with the star. And I think that pretty much covers all of the key points, unless there's something else that somebody else would like to add. Oscar, what do you think?
I was thinking of the square.
You can make what?
Square.
For what?
Like, if you need help or something, you can just write it down.
Sure. Yep, absolutely. I think that's good. If that works for you, write it down. Isaiah.
Can it be a key point of something you said today?
Absolutely.
You should always try to write down the as many square roots as you can.
Okay. So Isaiah is taking a key point that's related to our first half, and he's saying that, let me zoom in here a little bit. He's saying It helps to write down key points, or helps to write down key points. It helps to list perfect square roots. Or perfect squares. Let's just put it that way. It helps to list perfect squares. Okay? Cool. All right.